So welcome to folk who've joined on Zoom for another applied analytics seminar. And I think the seminar speaker this time hardly needs any introduction from me if you've been to these before, because he's done a lot of these actually. Thanasis Tsanas, who's a key machine learning person in College of Medicine at Edinburgh. So this, in a way, is one of a series, I suppose, for you, Thanasis, on relevance, redundancy, and complementarity. Thanasis, take it away. We'll give 45 minutes and then we have 15 minutes for questions, as you can see in the chat that Serena's put in. Thanks, Thanasis.
Great, thank you, Dave. First of all, I'll start with an apology. You might hear me a bit nosy. I just got diagnosed with COVID today. So if I don't sound as enthusiastic, it's because of fever and other things. It's not because I don't like the topic. So today, I'm talking about feature selection and about a new technique I developed a couple of years ago, really, but I only managed to publish it this year. It is my third talk in this series, and basically I've tried to build on the different concepts. So the first one was on a very generic, the full flowchart for how we analyze data. The second one was broadly on dimensionality reduction, and this one is on feature selection and specifically on the new algorithm. I think it is always useful to try to have the big picture in mind. So it is useful to think of a typical scenario where quite frequently you might start with some raw data. Typically, this would be in structured or unstructured format. Then you apply some algorithms to extract characteristics, so what we call features. And to that regard, we have discussed previously some ways to do it. For example, pattern recognition, time series, signal processing algorithms. If you're talking about non-structured data, this is going to be the NLP. But ultimately, what you try to do is extract those features from the raw data. And then we use the extracted features to map onto the outcome of interest. And that can be very varied. It really depends on the application. So very broadly, I've presented this slide before, but I really like it. The concept is you start with different raw data, which can be time series. In my case, most of my work is with time series. This can be physiological signals, could be activity, location, and so on. You apply, as you see in this arrow, different signal processing algorithms, and you put the data in that convenient format, this design matrix X that comprises N samples and M features. So today, we're going to start from this matrix. We presume that you have done the previous step either through measuring or through directly extracting those features, and basically this is where we start. Now, usually in most settings, you're into what we call the supervised learning setup, which practically means you have computed or you have extracted this design matrix X, which, as we said, has N samples and M features. This M typically is quite large for the kind of problems that we focus on today. And then most of the time, you also have an outcome. And that outcome is provided by the experts in that field. Quite frequently in medicine, this can be binary. So you can imagine cases where you have controls and people with a disorder, or it could be continuous, could be ordinal. Basically, you have different types of problems, and that is defined by what is this vector with the outcome, y. And I like to joke that really the university is paying me money to study this y equals f of x. So what I'm really trying to do day to day, and what I'm thinking about when I wake up in the morning, is find some way to associate the information extracted in the design matrix X with the outcome. So find some way to associate X information as a function of X to predict this Y. Now, a key part as we go along with this exploration is about identifying the key features we should be focusing on. This is the second box. This is the feature selection, and it precedes the last step, which is your favorite classifier or regressor. And I guess all of us here will have our favorite random forest, logistic regression, support vector machines, whatever statistical learner you like to apply in the end to really do the mapping. But before we get to that point, it is often crucial and critical to identify which features you want to actually identify from X in order to map onto the outcome. So once again, the flowchart I really like this kind of slides because it provides the key steps for analytics. Once you have presented the data in a design matrix and an outcome, the first step usually is about visualizing the data, applying some statistical hypothesis testing and exploring statistical associations. The third step, as you see here, which is the focus of today's talk, is about identifying the features that actually we're going to use to build the statistical learning model. And the last step is this bit about finding the functional mapping with your favorite statistical learner. So today, we're actually going to focus primarily on that part. And to some extent, we're going to see, of course, how this links with the statistical mapping. So let's talk about the problem. Everyone is excited about big data, and there's a lot of buzz and hype about big data, machine learning, deep learning, and all these bits, where a lot of people think that if you get a massive data set, then mainly your problem has been solved. But the truth is, that is when, if you have a massive data sets, that is when some of the problems start to kick in. One of the key problems that we call the curse of dimensionality basically means you have too many features. This M, if you remember in the design matrix, you have a number of samples, the number of features. The number of features potentially can be larger than the number of samples, which basically means the classical statistical learning tools are out of the window. You cannot really use them if the number of features are more than the number of samples. So we're going to revisit that kind of setting later on. All I'm going to say now is that this is a setting that is called fat dataset, and you're going to see a couple of examples later. So what's the problem really? I mean, if you think about having some participants and you try to see if they have cancer or they have some sort of disease, or you're talking about the stock market, surely if you can get lots and lots and lots of informative variables, that would be a good thing, right? And that is where the problem comes in. So if you have a lot of variables M, then intrinsically you reduce the signal to noise ratio in the data. You may have noticed that before I was very careful with the choice of my words. I said that those features would be informative. And that is something we're going to revisit in a bit as we move on. So many of the features that we have in typical data sets might simply be noisy or redundant, or they're not really predictive of the outcome. Or in fact, they might be predictive, but they might simply be replicas of other features or more weakly associated with the outcome. So we're going to see all these kind of different settings and challenges that really provide us with this classical problem of the curse of dimensionality, which frequently is actually detrimental to the statistical learning process, where you hope to actually have the statistical mapping to be very successful. So what is the solution? So if we know that the problem is that you have a very large number of features, then surely, intuitively, we can understand that reducing the number of features would actually be solving the problem. And of course, the key question then is, how do you do it? How do you go about reducing the capital M into something more manageable? Let's call it lowercase m. There are two ways to play this game. So one is by identifying some columns that you want to use. So essentially, you're going to get rid of, let's say, feature number 2, feature number 5, feature number 20, and so on. The alternative is if you apply what we call feature transformation. And I remember in my previous seminar in this series, I have actually talked about PCA and other techniques we can try to apply to actually find an informative way to combine different features and design new features that hopefully are more predictive of the outcome. Now, if some of you are coming from a clinical domain, one of the examples I like to provide that is really making sense to clinicians as an intuitive way is that clinicians have been long using the body surface area or the body mass index. And essentially, the BSA or the BMI are a function of height and weight. So essentially, what the clinicians are doing is that they have found some empirical way to combine height and weight into a single feature, which they call the BMR, the BSA, and they know that that feature is actually more predictive of, for example, cardiovascular status, as opposed to only looking at height or weight. So that clearly falls into this feature transformation space. Now, there are lots of problems there with feature transformation, and that is why we're going to focus today on feature selection. The key problem with feature transformation, like with principal component analysis and similar techniques, is that frequently you might not have interpretability. Contrary to that, with feature selection, you retain domain expertise precisely because the original features you have computed, they actually mean something to the experts in that domain. So if you can retain, for example, feature number 5 and feature number 20, then usually this feature number 5 and feature number 20 has a physical meaning to the experts in that domain. So for that reason, quite frequently, at least in the medical domain, we tend to prefer feature selection as opposed to feature transformation. In other domains where we do not care so much about interpretability and we care about performance and speed, like in finance, in those cases, we might be more prone to choose some of the feature transformation techniques. A further thing we have to consider is that in some cases, like for example, if you have very fat data sets, like with a microarray, where you might think that you have 100 participants and 10 or 20,000 genes, the only really practical way to approach this problem is with feature selection. Techniques like feature transformation will simply fail badly if you have such a very fat dataset problem. They will just not operate well. The other key thing that you have to consider with feature selection is that next time you go to collect data, if you have identified specific columns that you want to be focusing on, and you think that there is some money that you have to pay to collect each of those features, potentially you're saving also on money. So just to give you an example, you might think that feature number 1 is, for example, some blood test. Feature number 2 is something from a PET scan, and so on. So if you are next time going to identify that feature number 2 is not really predictive of the outcome in the presence of other features, then clearly not collecting it has saved you a lot of money because you do not need to apply and use this PET scan and so on. Contrary, if you are to apply feature transformation, you will still have to collect all the data, all the variables. So you can see there is a lot of arguments in favor of feature selection. So let's talk about an overview. I've put in on top the classical flowchart where you've generated some features from the raw data. This is the topic for today, how to identify a robust subset before you actually go on with the statistical mapping. One meaningful way to actually categorize feature selection techniques is down to what we call filters, which is the topic we're going to focus on today. And the other category is what we call wrappers. Let me briefly talk to you about these techniques, and then we'll get on with filters. So with filters, basically, you do not have a statistical learner involved. That means you're not going to integrate as part of the feature selection process the further step, which is the statistical mapping. By comparison with wrappers, you will actually need to employ a statistical learner, your favorite random forest, your favorite logistic regression, whatever learner you're trying to do. So you can easily imagine that wrappers are computationally much more intensive. And moreover, one of the key problems we have is that they may have what we call the feature exportability problem. In short, that means if you have to use support vector machines to select some features and identify perhaps through some extensive optimization process which features you're going to use, then it doesn't necessarily mean that if I were to use my own statistical learner, we're going to decide on the same features. And that is a problem. It is a problem because we're not really identifying the true features that are solving the problem. We're identifying something that is a function of the wrapper. Having said that, of course, wrappers have their own rightful place in the literature, because sometimes if you have made up your mind that you will use your SVM, random forest, XGBoost, whatever, and all you care is about employing things with that specific algorithm, then there is an argument that you want to optimize the features for that particular statistical learner. With wrappers and metaheuristics, the concept is we're trying to learn from nature. And the idea is that you can try to think of what the ant or the cuckoo or the whale and so on might do in order to optimize something. And then basically we have formed it in algorithmic settings. Now, these are metaheuristics and they are computationally very costly. Incidentally, probably most of you would have heard at least genetic algorithms. So if you haven't heard of all these ants and whales and cuckoos and all these things, probably you have heard of genetic algorithms. So they're all part of this big algorithmic family. So we're not going to be covering these wrappers. As I said, we will talk about filters because they're computationally simpler and very fast to work on. So some of the concepts I need to introduce is the first one is about parsimony. Essentially what that says is that you must try to find the simplest model that works well. So if you think that you are trying to build a statistical learning model, so this y equals f of x, you want to make this model as simple as possible, which means you're trying to minimize the number of features, but still try to maximize the accuracy or performance. I should probably not say accuracy, I should probably say the performance measure you have chosen to use. So if you think about you have all the features and each of the features, what we try to achieve is find the combination of the features that will actually maximize the information content. So what you try to achieve is identify the features that collectively actually are most predictive of the outcome. So the next question is how you can quantify those statistical relationships. And as usual, the answer is it depends. The simplest way that you can do it is by applying, for example, correlation-based approaches. So classical correlation coefficients like the Spearman or the Pearson and so on. And the limitation there is that you can only really capture linear or monotonic relationships. So if you imagine that there is some complicated statistical relationships between variables, that is something that cannot be really quantified using correlation coefficients. So a more generic approach that you can try to apply is with probability density based approaches. So many of you would have come across divergence metrics. They're more complicated, but essentially they rely on the full probability density function of the data, and therefore they are really capturing the full extent of the statistical association of the data. However, things are never as simple as that, because to get the probability density function correctly, particularly in the higher dimensional spaces, that means combining multiple features together, is actually a tricky problem. And for those of you thinking about, for example, probability density functions, there are questions about how you can optimize the bandwidth, how you can optimize joint bandwidth between 2, 3, or more variables together, what kind of assumptions you're going to use. I'm not going to go into too much detail, but basically computing the mutual information or some other divergence metric might be useful, but it is fraught with a couple of pitfalls that we'll have to carefully navigate. Very briefly, in terms of statistical associations, many of you would have come across the classical correlation coefficient, the Pearson correlation coefficient, which essentially is defined as the covariance between two random variables x and y, divided by the product of the variances, and then you basically square root it just to ensure that the units work out. And the correlation coefficient runs between -1 and 1, where basically you try to express the linear relationships between variables, and typically we tend to consider that if this is above 0.3, this is a statistically strong relationship. Now, moving beyond that, as I said, quite frequently, we may want to work with more generic relationships. And one way to do it is with the mutual information. So the mutual information, as you see here, y equals x, y. I equals x and y. So basically what you try to do is the mutual information between the variables x and y is essentially defined by this equation. It's the classical equation that you have for the Kullback library divergence, and it is adapted to have the mutual information. Now, the good thing with this approach is that you can quantify any extent of nonlinear statistical relationships. So with the asterisk, I've mentioned before that this can be quite tricky to compute, particularly in the high dimensional spaces, at least for working with the statistical relationship between two variables that is quite robust. But we're going to see a couple of problems when you try to generalize that. So let's talk about some of the key concepts, what we really try to achieve with feature selection, concepts like relevance, redundancy, and complementarity. Relevance essentially means you try to combine, you try to identify if there is a statistical relationship between the variable in X with the outcome, and that indicates, that can be quantified with classical linear correlation coefficients, mutual information, and so on. And basically, it indicates how a candidate variable is associated with the outcome. Redundancy means how two potential candidate variables might actually be contributing pretty much the same information, and therefore you may want to eliminate one of the two or more if you're talking about higher dimensional spaces. The third key concept is about complementarity, which is about combining the different variables, and you basically get the best than the sum of its parts. So let's talk with a couple of examples directly here. If you imagine that y is the outcome, and with this Venn diagram you have some overlap, you can clearly see that F3 much more overlaps with y rather than F1 and F2. So the first feature you might try to select is F3, then the second choice would be F1, and the F2 would be something that is what we call non-relevant. So you tend to discard it. With the concept of redundancy, you try to see if candidate features overlap substantially. And if they overlap, you may want to remove one of the pair. And the last one, the complementarity or conditional relevance, is about finding ways that you jointly consider variables. So for example, you might consider this combination log, where you do not really care about a single value on the log. You care about the combination, how you can get all of this to work together, where the sum of its parts is actually better. So the sum of its parts is actually better than just adding those parts. And we have ways to quantify that. That is basically the underlying concept of my algorithm. So let me briefly talk to you about some algorithms that have been very popular in the literature. The first one is the mRMR, so the minimum redundancy maximum relevance. And effectively, what you try to achieve here is you have the mutual information between a candidate feature and the outcome. That is what we call the relevance. And you try to minimize, as you see, the mean of the pairwise associations. So you try to find the mutual information between the feature and what you have already selected, so a candidate feature and something in the subset, and you take the average of that, and that is defined to be the redundancy. Now, this algorithm practically works very well, particularly if you have a large number of samples. You will see that it doesn't say anything about complementarity. So even theoretically, this is quite limited, but it is indeed one of the most successful algorithms in the literature. An extension of that algorithm, which I proposed back in my PhD, was basically pretty much the same concept, only that you substitute the mutual information with the Spearman correlation coefficient, and that can have some benefits, particularly with a small number of samples. In fact, in some cases, the mRMR Spearman can outperform the classical mRMR. Another very popular algorithm that has been very widely used in the literature is what is called relief. And with relief, what you try to identify is in a classical classification setting, you try to find the nearest hits, and the nearest misses. And that basically means you try to identify samples that have similar labels or different labels, identical labels or different labels. So on the basis of that, you can define terms, for example, in terms of the nearest hit distance and the nearest miss distance. And it is very similar conceptually to what you try to achieve with mRMR. You try to maximize the first part and minimize the second part. So my new algorithm is effectively an extension of mRMR and relief. So if you care to look at this part, effectively, it's pretty much the same concept like the mRMR. So I'm trying to find a computationally efficient way of the relevance, a computationally efficient way of the redundancy, and that last part is the complementarity. So the last part is the tricky part that I spent a lot of time. So essentially, the concept is the best result for identifying the features is really not only finding what is best for a single feature and minimizing redundancy, but actually considering what is happening in terms of the group. And I put this picture here because I got this inspiration while actually watching this movie, The Beautiful Mind, where the quote John Nash that he said this concept. And basically, I still remember when I heard this concept, that's when I stopped the movie and went back to MATLAB to actually code this up. So I've been trying for some time, and basically, I will not go into too much detail, but the idea is you try to express this complementarity concept in a computationally efficient way. So let's talk about how RRCT works and why I said it's computationally efficient. Well, if you remember that the mRMR, for example, operates on computing the mutual information, there are ways to actually compute it in going for a cheap way. So if you can transform the underlying variable and its density is more Gaussian-like, then the actual computation of the information theoretic approach, which is basically the equivalent of mutual information, is defined as -1 second, so basically minus 0.5 times the log of 1 minus the correlation coefficient squared. That is the definition of the classical mutual information if the underlying variable is Gaussian. Of course, things would be great if all the variables were Gaussian, because then we can buy this quite cheaply. But the concept is you can actually transform the underlying correlation coefficient, as you can see here, into something that is an information theoretic concept. And that is one of the key reasons for the success for my algorithm. The second thing is what we talked about, the complementarity. And I will not bore you with the equation here, but basically the concept is what you try to assess is the classical relevance that you can see, and then it's like the conditional relevance. So you try to find how much X is associated with Y conditioned upon Z. Practically, that means you try to find the association between a candidate feature with the outcome conditioned upon other variables. And that can be really powerful, as you can see here. So there are interesting ways and different concepts for how you can find these conditional probabilities. And the way I've defined it here is basically, again, a computationally efficient approach that you do not need to go with a full mutual information concept. So far, I've provided with an overview of different algorithms and how I try to come up with something that made sense to me based on information theoretic concepts. Let's talk about how you can actually try to assess the performance of feature selection algorithms. And the way to do it is either work with synthetic data, where you know the ground truth. And in that case, we have what we call the false discovery rate. In practice, that means you apply the algorithm, the feature selection algorithm you want to try, and then you try to see how many features were actually correctly identified and how many of them were falsely identified. So the false discovery rate ideally is 0. You run some problems, of course, with Markov blankets, which basically means if you have multiple Markov blankets within the dataset, then that is actually something that you may not be able to pick up. But then again, if you have synthetic data, this is something you can actually try to generate quite carefully. The second case is about real world data. And in that case, you do not really know which of the features truly correspond to predicting the outcome. And that is when you actually have to invoke a statistical learner. And as you invoke a statistical learner, you must have a loss function where basically you assess the accuracy or mean absolute error, whatever you want to choose to use. And basically, on the basis of the combination of the feature selection and the statistical learner, you're trying to infer if the feature selection was actually quite useful. And again, the problem there is that you may have feature exportability, meaning that depending on the statistical learner, you may have different results. So that is quite crucial to keep in mind. So in my paper, I've used 12 data sets. I've used classical synthetic data sets by some of the top people in this field. As you can see, they're all in classification mode because some of the competing algorithms I've used only operate in classification. My algorithm works both in classification and regression. And you can see I've tried to generate different kinds of problems with very few data, both samples and features, with cases where you might have a large number of samples, cases where you might have a fat data set, and so on. And then I had 8 additional real-world data sets. So let's try to see how the 20 different algorithms I've explored compare. So RRCT, this blue is my algorithm, and if I'm doing well, I should be at the bottom. So as we said, the false discovery rate is bad. It's an error metric. So basically, you want this to be 0. And just to try to translate what this means is that my algorithm, for example, for this particular data set, is identifying all 10 features correctly. So we do not define and do not find any wrong features within the 10 selections. Whereas other algorithms, as you can see, they tend to fail. For example, this one fails 60%. So this algorithm in this particular case is doing really badly. 60% of the features selected are actually not the true features. In the next synthetic dataset, this is a fat dataset. Once again, my algorithm works very well. So it is one of the big advantages of my algorithm that it can operate particularly well when you do not have a very large number of samples, but you have a very large number of features. However, all these are synthetic datasets, and someone might accuse me that I've tried to make things up. So let's see how things work in the real world. And again, you see a dataset, this Relaith, where basically you have 1427 samples and more than 4,000 features. So again, a very big dataset with a very large number of features. And you can see, once again, this is an error, so the lower the better. Once again, you can see that my algorithm that you can see here is actually outperforming the competing approaches, which in some cases perform really badly, as you can see, more than 40% misclassification. Another problem with ovarian cancer, once again, you can see my algorithm is performing extremely well. In most cases, like here, it is actually the global optimum. And yet, some more examples with fat data sets where you can see that my algorithm is not the best in this particular case, but still it is extremely competitive. The next thing is about computational efficiency, and what I've done is try to assess the time it takes to run the different algorithms, and you can see basically that for different data sets, my algorithm RRCT is about midway in terms of computational time it takes to run. That means that within a couple of seconds, you can get the actual correct number of features and correct true features most of the time at a fraction of the time that it might take for some computationally intensive algorithms like this YAML, which basically talks about Markov blankets directly. So the take-home message is that I've provided an algorithm, and I've tried to go a bit faster because we lost some time with me dropping out. I've introduced an algorithm that we think is quite powerful, really. It has strong theoretical underpinnings, and the good thing is that generalize well across different types of problems. It is one of the few algorithms that can be working computationally very efficiently, both with regression and classification problems. And the good thing is that intrinsically, the way I'm doing the computations, I can work with mixed type data. That means if my variables are continuous or discrete, my algorithm intrinsically takes that into account, whereas other algorithms in the literature will actually stumble. In terms of the code, so the paper is here. I provide the link so that you can download if you're interested. The code is actually in my GitHub, and the great thing is that it's really plug and play. So essentially what you run is you run the command RRCT in Python or MATLAB. All you have to insert is the design metrics and the outcome in your data set. and this will spit out the actual features that the RRCT is identifying as the correct features for that problem. I should probably say MATLAB is my native language, and it is computationally much faster than Python. However, for those of you working in Python, that is also available. Also, all the datasets I've used, both synthetic and real-world datasets, are available both in MAT and XLS format, so you can directly run it from the GitHub repository. If I can try to summarize, I probably would expect the question that is RRCT the best thing since sliced bread? And I would be the first one to say that it is not. It is very competitive. However, as a disclaimer, we always have to invoke the no freelance theorem. That basically means that there is not a single algorithm that would outperform competitors every single time. So RRCT is indeed performing very well for the vast majority of test cases I've tried, but there were some datasets that actually other algorithms were much better. Generally speaking, with feature selection, you must make some trade-offs, both in terms of algorithmic, you have to understand the dataset, you have to understand the implementations and how things might work. In some applications, as I mentioned previously, it may make sense to work with wrappers rather than with filters, and they might give you better results. However, filters are usually faster, and they're more clearly interpretable in the sense that they're not tied down to a specific statistical learner. The last thing that you should always remember is that with feature selection, we may or may not actually improve the prediction performance of your statistical learner, but we always improve the interpretability of that problem we're focusing on. I'll stop here with apologies for running slightly over time and my problem with the internet, and very happy to take any questions.
Great, thanks, Thanasis. We've got a little bit of time, and we have got, here's a question from Amar Shah. I'll shout it at Thanasis to sake of reading. Amar says, how and why did you choose the performance metric, the false discovery rate? Can you give us a sense of this metric in relation to sensitivity and specificity? And actually, he's had another thought, or in relation to precision recall?
Yeah, so these are fundamentally different concepts. So the false discovery rate is a concept about identifying the true features in a synthetic data set. It has nothing to do with the statistical learner. So the false discovery rate is a concept that we can only invoke in synthetic data sets where we know the ground truth in terms of the true features that are predictive of the outcome. By contrast, when we think about confusion matrix, sensitivity, specificity, M1, and so on, that actually is invoking statistical learners, and it's actually with, I guess, with the real world data. So you can apply with synthetic data, but these are very different concepts.
Great. Next, another question is from Ewan Harrison. Yes, there's two questions. How does it deal with non-linearity between predictor pairs or between X's and Y? That's the first one. I'll just give you the first one and then do the second one.
So the algorithm is actually taking into account implicitly non-linear relationships in the sense of that information theoretic concept. Now, if the underlying distributions are completely chaotic, then my algorithm might actually need some nudge, and that nudge might be that you're trying to Gaussianize the underlying distribution, and there are ways to do it, for example, the box Cox. So in that way, it does take into account the nonlinearity amongst variables, and particularly the last bit, if you remember, about the complementarity. So that bit is actually working directly with the iteratively regulated least squares, and that is actually intrinsically take that into account.
Good. Okay. And Ewan's second question was, any advice on optimizing feature selection across subgroups within a cohort? As in, if you want a model that performs well across n subgroups rather than being optimized for the entire population.
So often I feel now when we're doing these decision models, you know, the modeling happens, feature selection, you know, models are chosen and it comes to the end. And then you find that it doesn't work very well, for instance, in a particular ethnic subgroup, or it doesn't work very well in men compared with women, or it doesn't work very well in the elderly versus the young. And, you know, it's something I'm quite interested in trying to tackle right at the start of algorithm building, you know, and it may be that features are being discarded which are particularly useful for a small but important part of your cohort. And I was just wondering if you had thoughts on that, or whether it's nonsense, or I don't know.
Yeah, so actually, that is a key point, and there was some work that was published, I think, over the last 2 years, where effectively what people were doing is they were stratifying the data, as you said, on the basis of maybe ethnicities or males, females, and so on, and they were actually identifying the features for that particular stratified data set. Practically, that would mean that, for example, for females, you may have a different feature subset than you have for males. And in fact, that is something I've done for my work in Parkinson's. That is something that is clinically meaningful, because you can identify which features are really predictive for example, for males and females, and actually compare that. So we know this is something that is happening with stratified datasets, and only then working with these algorithms for that stratified dataset.
Okay, so I don't see any more questions in the chats, but can I ask a question, Thanasis? This is a curiosity question, because you mentioned at the very beginning that your primary interest was time series data, and to make things easily digestible, you didn't talk much about time, quite rightly, because that made it a very an easy talk to go along with. But does that make a difference to you in the analytics methods that you use, or does it just kind of factor in? It's just a bigger table.
You're talking about the first step with generating features, Dave?
Yeah.
So these are almost like different components for addressing a problem. The first one is about finding ways to characterize, for example, the time series. This could be my voice, my movement, whatever, my heart rate, whatever signal we have. It is about finding a convenient way to extract potentially useful information. And I guess maybe what I should have said at the beginning is that you can keep on extracting features, and that is what we're all doing. Keep on extracting features, start populating your design matrix, which will grow and grow and grow and grow, and have a very large design matrix with a very large number of features. So M is very large. And then basically you can try to apply iteratively this kind of techniques with feature selection, and then identify actually if the concept you have in the beginning to extract signal processing algorithms and extract those features made sense. That's in fact one of the iterative ways that we try to work across the setting, where you embed the feature selection with the part of extracting new features and then iteratively revisit it.
Good. Amar is back. He's saying, in relation to time series points, does this algorithm assume that each sample is IID, like most common algorithms do? Yeah,
indeed. So again, I have to clarify that these are different concepts. The first one is about the time series and the actual features we have. Yes, indeed. Every time we talk about getting the full PDF and so on, the underlying assumption is that those actual points are IID. And if they're not, we have ways to try to apply, for example, lead training or different ways that you can try to make them. But it is one of the key concepts you have to be careful. For example, I can give you an example where things might fail very badly. You might think of an extreme case where you have a lot of people with some disease, whatever you have, and you have one person that you continuously measured 1,000 times. And all the other people you have in the dataset were measured only once. So your algorithm, if you were to use all these 1,000 samples from a single participant, they're actually not IID. So you're going to bias the results by using all the samples. So you have to be careful that the actual samples are indeed IID.
Okay. So this is the point where I traditionally say, now's the time to, now's the time to last minute shout if anybody's got any last minute questions. Otherwise, we let Thanasis get back to his COVID convalescence. I think that would be humanitarian, actually, in this circumstance. I hope it's not driven you down.
I was diagnosed this morning, so so far it seems pretty classical with fever and so on. But yeah, let's see.
Yeah, terrific. Well, I hope it works out well for you. And I see Serena's put in a message in the chat for you to look at. The next analytics seminar, applied analytics seminars on the 7th, 4 p.m. So you can join for that one if you'd like. With that, I think the best thing to do is to thank you, Thanasis, and enjoy the rest of your day.
Thanks. Bye-bye.
Bye.